So our next speaker today, and I'm terribly sorry if I pronounce this incorrectly, is Kataro Ishikawa from Nagoya University, talking about exploring relationships between assembly bias and halo properties to walk dark emulator 2.
Oh. Thank you for the introduction. My name is Kataro Ishikawa, a PhD student at Nagoya University in Japan. Today I will talk about halo assembly bias toward a cosmological emulator in Roman era. To begin with, I will briefly introduce large-scale structure. It is a structure on a scale larger than that of galaxy clusters, and as you know, it is especially focusing on the late universe. And its galaxies are being formed in a struggle between gravitational interaction and accelerated expansion, aims to understand the nature of these components. To this end, there are so many galaxy surveys for cosmology in the world. This chronology represents the observation schemes that are ongoing and will launch. You can see that there are various surveys. Roman Space Telescope is obvious, and there are DESI and PFS as well. These leads to smaller statistical errors and relatively emerge from the effect of systematic errors. So we need a precise theoretical models considering systematic errors. For example, there are cosmological emulators. These can calculate the theoretical prediction of structural evolutions and as statistical quantities rapidly and accurately. Among systematic errors, there are roughly two types, observational and astrophysical ones. And in this talk, we especially focus on halo assembly bias in astrophysical one. And then I'll introduce linear halo bias to explain what halo assembly bias is. Due to the fact that 80% of matter is dark matter, so we'd like to understand dark matter distributions. However, we can only observe the galaxy distribution directly. Galaxy distribution directly, so we need to connect these relations. Dark matter halos, which collapse in high density regions, are needed to connect as well. On a large scale, we can write these relations via linear halo bias, just like these equations. And in this left figure, linear halo bias can be represented as a function mass, halo mass, and redshift. This right-hand side figure. Okay. This right-hand side figure shows output of a halo autocorrelation function at several halo masses from the emulator, which is based on n-body simulations. And you can see that there are several amplitudes when we select some halo masses. That is, linear halo bias primarily depends on halo mass. Then, what is halo assembly bias? To put it briefly, it is a secondary dependence of physical quantities other than halo mass. For example, there are concentration. These quantities are concentration and local overdensity and assembly histories. Today, we only talk about concentration. And for example, in this case, we focus on halos that have higher than typical collapsing mass. The same halo mass, same mass halos has different formation time, early forming and late forming. An early forming halo is a halo where the shapeness of initial density field is large, that is high concentrations, and can easily collapse without the help of surrounding environment. Therefore, the amplitude of clustering will be small. And on the other hand, an early forming halo has a low causes of initial density field, that is low concentrations, and can only be collapsed after the surrounding environment has grown to a certain extent. So that's why. So the amplitude of clustering will be large because it collapses with other low concentration halos in a larger amplitude region into a larger amplitude region in large scale mode. you can see that these features, when we measure halo, we measure halo at high mass regions. This figure shows that halo autocorrelation function, and the data in blue is measured using the full halo catalog. Then data in orange is using 25% of high concentrations. The data in then data in green is using 25% of low concentration halos. Extracting halo bias from previous figure, we can see that it varies as a function of halo mass. This left figure is from Wexler et al. 2006. The horizontal axis is virial halo mass initialized by a typical collapsing mass. The vertical axis is halo bias square based on the concentrations. The black line is the halo bias calculated by the halo with 25% of lower concentrations. And the red one is also 25% of high concentrations. And you can see that we confirm the same effect on our simulation data in right figure, and got smaller error bars with jackknife sampling. Okay, then, why is halo assembly bias important in cosmology? To answer it, I'll describe the dark emulator. Dark emulator is a cosmological emulator based on the n-body simulations that can calculate, that enables fast and accurate halo and matter statistical calculations. And there are several emulators in the world, and the dark emulator can only calculate halo statistics as far as I know. Of course, it can calculate the galaxy correlation function using halo occupation distributions. Its input parameters are mainly cosmological parameters and redshift and halo masses, but there doesn't consider assembly bias effect yet. This figure is from Miyatake et al. 2022, the validation test using HSC SDSS mock catalog with noiseless data vector for dark emulator 1. And these dashed lines are input values, and you can see that. And okay, so these contours are the result when we use the dark emulator, which doesn't consider the assembly bias effect. For example, the gray contour is the result from the simulation data using full galaxy catalogs, and you can see that it is unbiased from feature value. When we utilize MOX using the catalog that is selected by concentration value, the results are biased like blue and red contours if we don't use a template considering assembly bias effect. As I mentioned before, the halo assembly bias is confirmed on our simulation data. So our motivation is to consider the assembly bias effect on template models. Okay, I'll move on to implementing the halo assembly bias into the emulator. To reconstruct optimal mass concentration values, we sample mass and concentration threshold in 4D space due to cross correlations. We can point estimated values from these threshold ones. We also measure not only real space, but also redshift space, L equals 0.246, to reproduce the 2D correlations. And as I showed this slide, we use the feed-forward neural network to get an optimal mass and concentration threshold, just like interpolating between 4D spaces, mass concentration 1 and mass concentration 2 following these setups. We can mention that suppressing cosmic variance leads to the suppressing large-scale mode. After searching hyperparameters using Optina, which is an automatic hyperparameter optimization scheme, it shows that the scheduler is most important to optimize them. Okay, this is the results, preliminary results. And left figure represents the loss value as a function of epoch. From top to down, this represents the training loss, and validation loss and learning rate. On the right-hand side is a cross correlation from the test data. Upper one is XC over R, and lower one is the ratio emulator results to simulation data. The gray shaded region represents 1% error, and red line is average of test data. Good training is between 2 to 40 megaparsec over H, and larger error at smaller scale is due to the exclusion effect of halos. And larger one at between the 40 to 60 megaparsec is due to the beginning of cosmic variance, because cosmic variance that couldn't cancel out, because canceling cosmic variance named propagator method is valid only at larger scale. Okay, I'll summarize this talk. Today, the goal of this study is to implement halo assembly bias effect into the dark emulator 2. So we efficiently sample in multiple dimensional space, and we run the parameter dependence in 4D space by feed-forward neural network. And as a result, we achieve 1% accuracy between 2 to 40 megaparsec over H on feed-forward neural network. And next step, we consider redshift and cosmological parameters dependence. And also, I've worked to implement the dark emulator 1 into the COCOA, which is a Roman analytical pipeline with Tim, Elizabeth, Vivian, and Hironaro. So after considering assembly bias in dark emulator 2, we replace dark emulator 1 into 2. So we can solve the halo emulator to analysis Roman data. Okay, that's all. Thank you for listening.
Thank you very much. Do we have any questions in the audience?
On your third bullet, I just want to be clear on what you achieved 1% accuracy on. That's the halo mass cross-correlation function?
Cross-correlation function.
For halos over all mass ranges.
Yes.
And it's halo autocorrelation or it's halo mass cross-correlation?
Sorry, what?
Is it halo autocorrelation or halo
yes,
mass
halo
cross-correlation?
Cross-correlation.
Cross-correlation
Yes,
mass.
yes.
Okay,
So,
thank you.
Yeah, you can see that several masses.
Any other questions? If not, let's please thank our speaker again. And we now have coffee, and so we'll see you back here at 3 o'clock. Thank you.